In the study of conductors in electrostatic field, we applied Gauss' law stating that the divergence of the electric field strength E is given by its source charge density ρ over the vacuum permittivity epsilon naught, and expressed the field strength as the negative gradient of the electrostatic potential phi to prove Green's reciprocation theorem. As a result, we obtained Poisson's equation for the potential in vacuum stating that the Laplacian of the potential phi is equal to minus the electric charge density ρ over the vacuum permittivity epsilon naught. In general, this equation must be solved as a boundary value problem for the volume of interest with a boundary consisting of the interfaces of different media or conducting surfaces. This can be challenging because normally only the spatial distribution of the source charge is given, whereas the distribution of the induced charges over the conductive surfaces specifying the boundary condition for the problem depends on the potential over the volume of interest, that is, on the solution of the boundary value problem. The most effective approach to solve boundary value problems in electrostatic is based on the principle of superposition already introduced as one of the consequences of Green's reciprocation theorem. Due to this principle, the electrostatic potential phi can be constructed as the sum of a particular solution phi sub p of Poisson's equation for the specified volume charge density, and a general solution psi of Laplace's equation chosen so that the total potential satisfies the specified boundary conditions. The method of images applies such a superposition of the electrostatic potentials in the case of one or more point charges or the distribution of charge along lines in the presence of boundary surfaces, such as conductors or dielectrics. For a few simple geometries, we can replace the actual boundary value problem over the volume of interest V by another problem solved over an enlarged region of the union of V and V' without boundaries, where we place a small number of charges of appropriate magnitudes at appropriate positions in the volume V' external to the region of interest V such that they can simulate the required boundary conditions. In the example shown here, the boundary value problem is to determine the potential phi of a point charge Q in the vicinity of a conductor, either grounded or held at constant potential, which represents a boundary condition for Poisson's equation being solved over the volume V. By applying the method of images, we replace this problem by another one over the enlarged domain of the union of V and V', where we placed a point charge Q' in the complementary volume V'. We can choose the magnitude of Q' and its position in the volume V' such that we can simulate the boundary condition in the original problem. These fictitious charges external to the volume of interest V are called image charges, and their potentials psi are the general solutions of Laplace's equation inside the volume V that guarantee that all boundary conditions are satisfied for the general solution phi of Poisson's equation over the volume V given by the sum of its particular solution phi sub p and the potential psi. Once the image charges are known, the problem is solved as if the boundary surfaces were not present but with a charge distribution composed of the original charges plus the image charges in the enlarged volume of the union of V and V'. Now we apply the method of images to describe the electrostatic field between charges and conducting surfaces. We start with the simplest example as far as the geometry of the field considered, which is a uniformly charged infinite line and a pair of such lines. We already determined the electric field E due to a uniformly charged infinite line of charge density of lambda at a given point P in the vicinity of the charge line, and we found that its magnitude is equal to lambda over 2 pi times epsilon naught times the distance r between the point P and the line. For a positive charge distributed over the infinite line, the electric field E points radially outward from the line, exhibiting a cylindrical symmetry around it. Because of this symmetry, the field strength E given by the negative gradient of its electric potential phi reduces to minus the derivative of phi with respect to the distance r. Then the electric potential phi is given by minus the integral of the magnitude of E, that is lambda over 2 pi times epsilon naught times r with respect to the distance r. This gives a potential of minus lambda over 2 pi times epsilon naught, times the natural logarithm of the distance r over an arbitrary reference distance r naught of the constant of integration chosen as the null point of the potential. The result shows that the equipotential surfaces of the electric field are cylindrical surfaces around the charged lines for given radii r. Evidently, the electric field lines are perpendicular to these surfaces at each point. Now we consider the electric field due to two parallel uniformly charged infinite lines of opposite polarity of plus and minus lambda, where the distance between the two lines are given by 2 times x0 in the coordinate system with the origin at the midpoint of the two line charges. The xy plane is perpendicular to the line charges and the distance of each charged lines from the origin is equal to x0. We want to determine the potential phi of the field produced by the two charged lines at an arbitrary point P, where the distances r sub plus and r sub minus of the point from the line charges are determined by the Pythagorean theorem. That is, r sub plus is equal to the square root of the square of the y coordinate of the point plus the square of the sum of the x coordinate of the point and x0, and our sub minus is given by the square root of y squared plus the square of the difference between x and x naught. The potential phi of the field due to the two charged lines at the point P can be constructed by applying the principle of superposition of the individual solutions phi sub plus and phi sub minus of the Poisson's equation given for each of the line charges. If we insert the expression obtained for the potential of an individual line charge into the sum, we can write phi as minus lambda over 2 pi times epsilon naught, times the natural logarithm of r sub plus over r naught, plus lambda over 2 pi times epsilon naught, times the natural logarithm of r sub minus over r naught. As a result, the potential at the point P is given by minus lambda over 2 pi times epsilon naught, times the natural logarithm of r sub plus over r sub minus, where the null point r naught is cancelled out. The equipotential surfaces consist of the points for which the ratio of the distance r sub plus to the distance r sub minus is a constant, say the square root of k, where k is an arbitrary non-negative number. This condition is equivalent to the one stating that the square of r sub plus is equal to k times the square of r sub minus. By substituting the coordinate expressions of the distances into this condition, we can write that y squared plus the square of the sum of x and x naught is equal to k times y squared plus k times the square of the difference between x and x naught. We can expand the squares of the sum and the difference of x and x naught, and group the terms with the coordinates x and y on the left-hand side of the equation, leaving a constant in the right-hand side. If we divide the resultant equation by 1 minus k, we obtain a simple expression stating that x squared plus y squared minus 1 plus k over k minus 1 times 2 times x naught times x, is equal to minus x naught squared. By completing the square in the left-hand side, we can write the equation stating that the square of the difference between x and 1 plus k over k minus 1 times x naught, plus y squared, is equal to 4k times x naught squared over the square of 1 minus k. Now we introduce the notation x sub c defined by 1 plus k over k minus 1 times x naught, and the notation y sub c simply set to 0. The notation r sub c can also be defined by 2 times the square root k times x naught over the magnitude of 1 minus k, and we substitute the three constants into the last expression. As a result, we obtain an equation stating that the square of the difference between the x-coordinate and x sub c, plus the square of the difference between the y-coordinate and y sub c, is equal to the square of r sub c, which is the equation of a circle in the xy plane. The center of the circle is defined by the coordinates x sub c and y sub c, whereas its radius is given by r sub c. Then we have found that the equipotential surfaces for the electric field due to two uniformly charged infinite lines are infinite cylindrical surfaces around both of the line charges. The axis of each cylindrical surface lies in the plane y equals 0 and its distance from the origin is given by x sub c. For a fixed distance x naught, the constant k determines both the radius r sub c of each equipotential surface and its position x sub c. If k approaches 1, then the centers x sub c of the two sets of equipotential surfaces around the line charges with opposite polarities tend to plus or minus infinity, and their radii r sub c also diverge. As a result, the plane x equals 0 is an equipotential surface and the limit of k approaching 1. The range of k between 0 and 1 describes the equipotential surfaces for x less than 0, that is in the left-hand side of the plane x equals 0, and the values of k greater than 1 represent the equipotential surfaces in the right-hand side of the plane x equals 0. The electric field strength E of the field due to the two line charges is given by the negative gradient of the potential phi with a cylindrical symmetry around the line charges, and we only need to determine the partial derivatives of the potential phi with respect to the x and y coordinates. Since the potential is proportional to the natural logarithm of r sub plus over r sub minus, we compute the derivative of this expression where the prime denotes the partial derivative with respect to either x or y. By applying the chain rule for the differentiation of composite functions, we can write the derivative as the product of the derivative of the natural logarithm of the inner function r sub plus over r sub minus, and the derivative of the inner function. That is, we have r sub minus over r sub plus, times r sub plus prime times r sub minus r sub plus times r sub minus prime over the square of r sub minus. This expression can be written as 1 over the product of r sub plus squared and r sub minus squared, times the difference between r sub plus times r sub plus prime times r sub minus squared, and r sub plus squared times r sub minus prime. Now we use the definitions of the distances r sub plus and r sub minus between any given point in the line charges, and write the partial derivative r sub plus or minus with respect to the x-coordinate as x plus or minus x naught over r sub plus or minus. Similarly, the partial derivative of r sub plus or minus with respect to the y-coordinate is equal to y over r sub plus or minus. These expression can be inserted into the partial derivatives of the natural logarithm of r sub plus over r sub minus with respect to the x and y coordinates. This gives 2 times x naught over the product of r sub plus squared and r sub minus squared, times the x naught squared minus x squared plus y squared, and minus 4 times x naught over the product of r sub plus squared and r sub minus squared, times x times y. If we substitute these derivatives into the partial derivatives of the potential phi, we can write the electric field strength E at a given point as the linear charge density lambda over pi times the vacuum permittivity epsilon naught, times the distance x naught of the charged lines from the origin over the product of the squares of the distances r sub plus and r sub minus between the point and the charged lines, times a vector with the x component given by x naught square minus the square of the x coordinate of the point plus the square of the y coordinate of the point, and with the y component given by minus 2 times the product of the x and y coordinates. The direction of the electric field is perpendicular to the equipotential surfaces which we determine quantitatively. Since the direction of the electric field strength is the tangent to the electric field lines, the derivative of the y coordinate with respect to the x coordinate is equal to the y component of the field strength E over its x component. By inserting the expressions obtained for the components of the electric field E into this equation, we can write it in the form where the differential of y over y is equal to minus 2 times x times the differential of x over x naught squared minus x squared plus y squared. If r denotes the distance of a point from the origin in the xy plane, that is r squared is equal to the sum of x squared and y squared, then we can convert the equation into another one stating that the differential of the natural logarithm of y is equal to the differential of r squared over x naught squared minus r squared. Here the right-hand side is given by minus the differential of the natural logarithm of the difference between x naught squared and r squared. This separable differential equation can readily be integrated by choosing the constant of integration as 2x naught times cotangent alpha, where alpha is an arbitrary number. As a result, we obtain an equation stating that 2x naught times cotangent alpha times y is equal to minus x naught squared plus r squared. If we substitute x squared plus y squared into r squared and complete the square for the y coordinate, then the result is an equation stating that the square of the x coordinate plus the square of the difference between the y coordinate and x naught times cotangent alpha is equal to x naught squared over the square of sine alpha. This expression is also an equation of circles with the centers lying on the plane x equals 0, whereas the y coordinate of the centers and the radii of the circles are determined by the distance x naught and the constant alpha. Then the equation shows that the electric field lines are circles in the xy plane with the centers on the plane x equals 0, where these circles form cylindrical surfaces running parallel with the charged lines. The intersections of these cylindrical surfaces with the equipotential surfaces, that is the intersections of the two families of circles, demonstrate that the electric field is everywhere perpendicular to the equipotential surfaces, as expected. We have described the electric field due to two uniformly charged infinite lines of opposite polarity running parallel with each other in order to use this problem when we determine an electric field with cylindrical symmetry by applying the method of images. The first example for such a field geometry is the electric field due to a single uniformly charged infinite line near an infinite conducting plane parallel with each other. If we consider the electric field due to an uniformly charged infinite line of charge density lambda at the distance x naught from a conducting plane, then we find the following. The electric field lines emanate from the positive electric charge distributed along the infinite line and terminate at the induced negative charge distributed over the infinite conducting plane. For an electric conductor, these field lines are perpendicular to the planar surface at which they terminate while pointing in the direction opposite of the surface normal. The equipotential surfaces are infinite cylindrical surfaces about the line charge due to the symmetry of the distribution of the charges along the line and over the surface. If we compare the geometry of this electric field with the one in the left-hand side of two uniformly charged infinite lines of opposite polarity at a distance 2 times x naught from each other, then we can see the same distribution and orientation of the electric field lines in space. Motivated by these findings, we will apply the method of images to determine the electric field due to the uniformly charged infinite line near the infinite conducting plane. Since the volume of interest V enclosing the line charge has the boundary at the conducting plane, we need to solve a boundary value problem for Poisson's equation with a source charge given by the linear charge density lambda. Following the method of images, we replace the boundary value problem with a problem where we extend the volume V with the volume V' and place an image charge distribution in V', that is a line charge of the constant charge distribution minus lambda at the distance x naught from the boundary of the volume V. When we derived the potential phi of the pair of infinite line charges with opposite polarity, we applied the principle of superposition and constructed phi as the sum of the individual potentials phi sub plus and phi sub minus due to the positively and negatively charged infinite lines. The potentials phi sub plus and phi sub minus at a given point depend on the distances r sub plus and r sub minus between the point and the line charges. If the domains of these potentials are restricted to the volume of interest V, then the potential phi sub plus is the solution of Poisson's equation with the source charge density ρ sub plus given by lambda times the Dirac delta depending on the x-coordinate plus x naught times the Dirac delta depending on the y-coordinate. This distributional charge density in Poisson's equation is integrated over the volume V. The potential phi sub minus restricted to the volume V satisfies Laplace's equation over V since its source charge density is distributed over the complementary domain V prime. As a result, we can identify the potential sub plus restricted to the volume V as the particular solution phi sub p to Poisson's equation with the source charge density ρ sub plus without the boundary condition. The potential sub minus restricted to the volume V is identified as the function psi satisfying Laplace's equation chosen such that the sum of phi sub p and psi gives the solution phi to the original problem. In other words, if the potential phi sub plus due to the uniformly charged infinite line and the potential sub minus due to the image line charge in the complementary volume are restricted to the volume V, then their sum is equal to the potential phi due to the uniformly charged infinite line at a given distance from a conducting plane. Since the potential in this problem is the same as the one due to the pair of uniformly charged infinite lines with opposite polarity, the electric field E at a given point near the infinite line in the infinite conducting plane is also the same as the one derived in the previous problem. Here r sub plus denotes the distance between the point and the line charge, whereas the distance r sub minus between the point and the image charge can be interpreted as a shorthand notation in the formulae. Now we compute the electrostatic force per unit length exerted on the line charge by the induced negative charge over the conducting plane. The force F per unit length L exerted on the infinite line charge is equal to the product of the uniform linear charge density lambda and the electric field E evaluated at the line charge, that is at x equals minus x naught and y equals 0. Although the components of the electric field strength evaluated at the line charge have indeterminate forms, and L'Hospital's rule cannot be applied for functions of two variables to evaluate the limits in general, we can use the principle of superposition to derive the electrostatic force acting on the line charge. We subtract the electric field created by the charged line itself from the net electric field and compute the force produced by the field due to the image line charge of density minus lambda at the distance 2 times x naught from the real line charge. Since the magnitude of the field strength is given by lambda over 2 pi times epsilon naught times the distance between the two charged lines, the magnitude of the force F per unit length L is equal to the square of the linear charge density lambda over 4 pi times epsilon naught times the distance x naught between the charged line and the conducting plane. The force points in the direction of the x-axis towards the infinite plane with the uniform distribution of induced negative charge. Let us also determine the surface charge density sigma of the induced charge over the conducting plane given by x equals 0. We already saw that the surface charge distribution over the surface of a conductor is given by epsilon naught times the directional derivative of the potential along the surface normal. Since the electric field is perpendicular to the conducting plane, the directional derivative of the potential is equal to minus the x component of the electric field strength E evaluated at x equals 0. If we evaluate the expression obtained for the field strength at x equals 0, we can write sigma as minus lambda over pi, times x naught divided by the sum of y squared and x naught squared. The total charge per unit length on the plane denoted by lambda with the subscript tot can be obtained if we integrate the surface charge density at x equals 0 from minus infinity to infinity with respect to the y-coordinate. If we substitute the expression obtained for sigma into the integral, we will have minus lambda times x naught over pi times the integral of 1 over y squared plus x naught squared with respect to y. By factoring x naught squared out from the integral and substituting the variable y of the integration by y over x naught, we perform the integration which gives lambda times x naught over pi, times the primitive function 1 over x naught times the inverse of tangent y over x naught evaluated at the limits minus infinity and plus infinity. The evaluation of the primitive function gives minus lambda, that is the total charge per unit length on the plane is just equals the image charge. We can use the example of the pair of infinite line charge of opposite polarity in the method of images to solve other problems where the equipotential surfaces are infinite cylindrical surfaces. The first example for such a geometry is an infinite line charge of uniform charge density lambda at a distance x sub plus from the center of infinite conducting cylinder of radius r, where the line charge is either outside or inside the cylindrical surface. If we inspect the geometry of the electric field produced by the infinite charged line and the induced charge on the infinite conducting cylinder, then we find that the field lines starting from the line charge and ending at the cylinder are perpendicular to the surface of the conductor, whether they are running outside or inside the cylinder. We note that in the latter case the line charge is a free electric charge enclosed by the conducting cylinder, therefore the electric field does not vanish there. The cylinder with the induced charge over it is an equipotential surface, and all the equipotential surfaces are infinite cylinders either enclosing the line charge and the conducting cylinder in two separate families, or enclosing the line charge inside the conducting cylinder. This shows that the geometry of the electric field is the same as the one produced by the two line charges of opposite polarity over the spatial domain of interest, and we can apply the method of images. We therefore replace the boundary value problem over the volume of interest containing the charged infinite line with the boundary at the infinite conducting cylinder by an enlarged volume with an image line charge of opposite polarity. The volume of interest V in the first case is the whole space excluding the cylinder, whereas in the second case V is the space inside the cylindrical surface. Now we extend the volume of interest by supplementing the volume V with its complementary domain V' so that in the union of the volumes V and V' will cover the whole space. In the first case, the complementary volume V' is the domain inside the cylinder, where we place the image line charge of charge density minus lambda. In the second case the complementary volume V' is the whole space outside the cylinder where the image line charge minus lambda is located. The line charge and an image line charge at the distance 2 times x0 produce the same electric field in the volume of interest V as the line charge with the cylinder. We only need to determine the distance x0 for a given distance between the line charge and the center of the cylinder and a given radius of the cylinder. Since the cylinder is an equipotential surface, we can apply the equation describing the circular sections of the cylindrical equipotential surfaces derived for the pair of line charges with opposite polarity. This equation states that the center of these cylindrical surfaces is on the y-axis with the coordinates x sub c given by 1 plus k over k minus 1 times x0, and the radius r sub c of the cylindrical surface is equal to 2 times the square root of k times x0 over the magnitude of 1 minus k. Here the value of k specifies the given equipotential surface. There must exist a value of k for which the equipotential surface in the method of images coincides with the conducting cylinder in the boundary value problem. For such a value k0, we have a condition in the first case stating that the distance x sub plus between the line charge and the center of the cylinder is equal to the sum of the distance x0 and the x-coordinate of the center. In the second case, the condition states that the distance x sub c of the center from the origin is given by the sum of the distances x0 and x sub plus. We can combine these two conditions into one equation and substitute the expression for the x-coordinate of the center into the result. Then we find that the distance x plus is equal to 1 plus k0 over k0 minus 1, times x0, minus or plus x0. Here we use plus for the first case and minus for the second one. Another condition holds for the radius r of the cylinder telling us it is equal to 2 times the square root of k0 times x0 over the magnitude of 1 minus k0. If we raise these two equations to the power of 2 and divide the first equation by the second one, then we can write that x sub plus squared over r squared is equal to the square of the quantity 1 plus k0 plus or minus k0 minus 1 in parentheses, over 4 times k0. After having simplified this expression, we obtain 1 over k0 for the first case and k0 for the second one. As a result, we derive the condition for the parameter k0 that determines the equipotential surface corresponding the conducting cylinder for a given distance between the line charge and the center of the cylinder, where the center and the radius of the cylinder are also given. This condition states that k0 is equal to the ratio of x sub plus squared to r squared for the first case, or its reciprocal for the second one. The second condition holds for the distance x0, which we obtain by inserting the first condition into k0 appearing in the square of the radius r and solving the result for x0. Then we can write that x0 is given by plus or minus x sub plus squared minus r squared over 2 times x sub plus. We can also calculate the distance x sub minus between the image line charge and the center of the cylinder, for which we can write that the distance x sub c of the center from the origin is equal to the sum of x0 and x sub minus for the first case, and express x sub minus as the sum of x0 and x sub c for the second one. If we combine these two equations into one and substitute the expression obtained for x sub c into the result, we can write that the distance x sub minus is given by 1 plus k0 over k0 minus 1 times x0, minus or plus x0. By inserting the expression obtained for x0 into the right-hand side of this equation, we find that the distance x sub minus of the image line charge from the center of the cylinder is given by the square of the radius r of the cylinder over the distance x sub plus of the line charge from the center. In other words, the scaling factor between the distances of the line charge and its image from the center of the conducting cylinder is given by the square of the radius of the cylinder. We can also determine the electrostatic force per unit length exerted on the charged infinite line by the charge induced over the surface of the conducting cylinder in the same way as for the line charge near the conducting plane, since both the plane and the cylinder were replaced by an image line charge of opposite polarity. Then the direction of the force exerted on the line charge by the image points towards the image line charge in the plane y equals 0, and the magnitude of the force F per unit length L is equal to lambda squared over 4 pi times epsilon naught times x naught. If we substitute the expression obtained for x naught into the right-hand side of the equation, then we can write the magnitude of the force per unit length as the square of the linear charge density lambda times the distance x sub plus between the line charge and the center of the cylinder, over 2 pi times the vacuum permittivity epsilon naught times the difference between the square of the distance x sub plus and the square of the radius r of the cylinder. This formula becomes singular if the distance x sub plus is equal to the radius r, that is when the line charge is on the surface of the cylinder. If we replace the charged infinite line by an infinite conducting cylindrical surface, then we will have another example for an electric field with cylindrical symmetry. In such a scenario, we consider the electrostatic field due to the charge distributed over two infinite conducting cylindrical surfaces of radii r sub 1 and r sub 2 having their centers the distance x sub 1 apart. The cylinders can either be adjacent, as seen in the figure, or the cylinder of smaller radius can be inside the other one of bigger radius. If any of the cylinders has the charge q, then opposite charge minus q is induced over the surface of the other one, and the electric field lines will emanate from the positively charged cylinder and terminate at the negatively charged one. As in the previous examples, the field lines starting from or ending at the surfaces of the conductors are perpendicular to the surfaces and the conducting cylinders are equipotential surfaces. Then we have the same geometry over the domain of interest for the electric field produced by the two charged cylinders as in the case of the two uniformly charged infinite lines with opposite polarity. In this boundary value problem, the volume of interest V is either the space enclosing the two infinite cylindrical surfaces and excluding their interior, or the space between the two cylindrical surfaces. In both the cases we have two separate boundary conditions for the volume V. Now we apply the method of images by extending the volume of interest with the two domains excluded from the boundary value problem, and placing two image line charges of opposite polarity in each complementary volume. We assume that the volume integrals of the uniform charge densities of opposite polarity of the charged lines give the total amount of the charge q and minus q of the cylinders. In the first case, we extend the volume of interest V with the interior volumes V' and V" of the cylinders, and place the charged infinite lines of charge densities lambda and minus lambda on the x-axis inside the infinite cylinders with polarities corresponding the directions of the field lines in the boundary value problem. In the second case, the complementary volumes V' and V" are the interior of the smaller cylinder and the domain outside the bigger one, respectively. Then the boundary value problem is replaced by the problem involving only two infinite line charges of opposite polarity, and its known solution over the union of the volumes V', V' and V" gives the solution to the boundary value problem restricted to the volume of interest V. The task is to determine where to place the line charges to obtain the same electric field as the one produced by the charged cylinders in the domain of interest. In order to obtain the condition for the position of the line charges equivalent to the charged cylinders, we will compute the distances x sub 1 and x sub 2 of the line charges from the centers of the corresponding cylinders. In the first case, the distance x sub plus of the line charge lambda from the center of the opposite cylinder is given by the difference between the distance d of the centers of the cylinders from each other and the distance x sub 1 of the line charge from the center of the cylinder enclosing the line charge. Similarly, the distance x sub minus of the line charge minus lambda from the center of the opposite cylinder is equal to the difference between the distance d and the distance x sub 2 of the line charge from the center enclosing the line charge. In the second case, the distance sub x plus between the positive line charge and the center of the outer cylinder is given by the sum of the distance x sub 1 between the line charge and the center of the inner cylinder and the distance d. We can also express the distance x sub minus between the negative line charge and the center of the inner cylinder as the distance x sub 2 between the line charge and the center of the outer cylinder minus the distance d. The conditions for the positions of the image line charges follow from the one obtained in the previous example with a single line charge and a single cylinder. The first condition states that the distance x sub 1 between the center of the cylinder of radius r sub 1 and the positive line charge is equal to the ratio of the square of the radius r sub 1 over the distance x sub minus between the negative image line charge and the center of the cylinder. If we substitute the results obtained for the distance x sub minus in the two cases into this ratio, The condition tells us that x sub 1 is given by the ratio of r sub 1 squared to d minus or plus x sub 2, where the upper sign is for the first case and the lower sign is for the second one. The second condition states that the distance x sub 2 between the center of the cylinder of radius r sub 2 and its negative line charge is equal to the ratio of the square of the radius r sub 2 over the distance x sub plus between the positive image line charge and the center of the cylinder. By inserting the expressions obtained for x sub plus into this equation, we can write the ratio as plus or minus r sub 2 squared over d minus x sub 1. The two conditions can be solved for the variables x sub 1 and x sub 2, which gives two second-order algebraic equations. The first one states that x sub 1 squared, minus 2 times a quantity denoted by b sub 1 2, plus r sub 1 squared is equal to 0, whereas the second one states that x sub 2 squared, minus or plus 2 times b sub 2 1, plus r sub 2 squared is equal to 0. The quantity b sub ij is just the shorthand notation of d squared plus r sub I squared minus r sub j squared over 2 times d, where the indices I and j equal 1 and 2 and they are distinct. Then the positions of the line charges are determined by the roots of these equations, and the distance x sub 1 between the positive image line charge and the center of the cylinder of radius r sub 1 is equal to b sub 1 2 minus or plus the square root of the difference between b sub 1 2 squared and r sub 1 squared, and the distance x sub 2 of the negative image line charge and the center of the cylinder of radius r sub 2 is given by minus or plus b sub 2 1 minus the square root of the difference between b sub 2 1 squared and r sub 2 squared. As a result, by applying the method of images for two infinite conducting cylinders of given radii at a given distance from each other, we can replace the two cylinders by two line charges of opposite polarity at given distances from the centers of the cylinders, where the distances can be determined from the radii of the two cylinders and the distance between them. Then the force F per unit length L exerted on the first cylinder by the field due to the opposite image charge minus lambda is equal to lambda squared over 4 pi times epsilon naught times the distance given by the difference between plus or minus d minus x sub 1 and x sub 2. If we insert the expressions obtained for the distances x sub 1 and x sub 2 into the right-hand side, the force per unit length can be written as the square of the linear charge density of the image charges over 2 pi the vacuum permittivity epsilon naught times the square root of the difference between b sub ij squared and r sub I squared, where the indices I and j are equal to 1 and 2 for the first case and 2 and 1 for the second one.